let's get started. So Favonia has an announcement about homework due date. All right, so everyone got that? You should put it on the piazza, actually. Yeah. I'll erase that. Gone. Okay. All right, so where we were last time is we got to the point as we were looking at the identity type. And in particular, we were looking at the idea that maps are what is sometimes, well, by the end of this lecture, we'll make good sense about this. But let's say, right now we'll say maps preserve, okay, we'll leave it like this, preserve proofs of identity or identifications. And I called this functionality. It's a version of, it's an enriched version of functionality, and in a little bit I will actually be able to say that that represents an even stronger property called functoriality, but right now let's say functionality. So what we end up saying is if we have, for example, F is a map from A to B where these are closed types, and we have some proof that some two arguments in A are equal, or there's an identification between them, then there's an action, there's a thing called app, FP, which sometimes in informal notation people will abuse notation and just write that as F of P. Depending on the situation, that can be not confusing or confusing, so I'll try to stick with that at least for the time being, which is a proof that in B, f of A is f of A prime. So if you read it as a logical principle, it says the obvious thing that says if A is equal to A prime, then let's say true, let's write it like that to emphasize what I'm doing, the logical principle, then f of A equals in B f of A prime is true, which is certainly a condition you would expect of any notion of equality. So if this is supposed to be representing equality, then you would expect to be true. So that was sort of property number one, which I called functoriality. And then the other thing that we talked about was a kind of functionality as well for families, which is the transport property. So transportation. And the idea here is if we have a closed type and a family of types over them, then and we also have some path in as we well, let's write it like this to be careful for the time being. A equals A prime in the base space, as it's sometimes called, the indexing type of the family, and we have two equal things, then in a certain sense we should expect, at least by analogy with what I've written here, that there ought to be some relationship between B of A and B of A prime. And what I described is that there's a transport property, which could be thought of as parameterized by this, and which, when applied to P, gives us a function that takes, if I write it like that, it looks a little better, B of A to B of A prime. Now this function will have some useful properties that we'll develop a little bit shortly, but that will end up saying that it's an equivalence. But right now, let's just say we have a function, a transport function that goes from B of A to B of A prime. And you'll notice that at a minimum, because of the symmetry of equality, there's also, by putting P inverse here, there's also a transport that goes back the other way. So therefore, you would naturally begin to ask, well, what happens if I go over and back? And then we'll talk about that a little bit later. Okay, so this was the notion of the transport property, and it's a kind of functionality for families, you might call it. Okay, so let's go family functionality. And in fact, that's the origin of this term comes from when we were, well, I'll explain that later. So this is a kind of family functionality. And from the point of view of logic, the logical reading of this thing is, the logical reading of this thing is, says, well, for such a situation, if you give me, if it's true that A is equal to A prime, then, well, I would like to be able to say something like B of A is, but let's write it like this, okay, and B of A is true, so let's put it this way, then B of A prime is true, if you read it as a principle of logic. And in fact, by taking advantage of the symmetry of equality, we could replace this in a logical reading by saying if A prime is true, then B is logically equivalent to, now I've run out of useful symbols, so I need to write something for logically equivalent, so let's write this. B of A is interprovable with B of A prime. In other words, this is true implies this is true, and this is true implies that is true. So as a principle of pure logic, it just says, again, the same sort of idea, that we have a decent notion of equality because we have something that is somehow varying over A, and therefore equal elements of the thing it's varying over should give us, at least from the point of view of logic, equivalent, logically equivalent. So this at this point means just, we can ask more, but right now we'll think of just logically equivalent. That's what I want to write here. Okay. And what I'm trying to get you used to, because I'm assuming that this isn't familiar to you, what I'm trying to get you used to is I'm pushing toward the slightly different flavor of the way you write things in a proof relevant in type theory, where proofs are relevant. So in conventional logic, proofs are not relevant. That is, there is no idea of proofs as mathematical objects. So if you were dealing with logic, if you were dealing with conventional logic, you would say, well, if I have a proposition, a predicate over A, that's what this would be saying, then if I give you equal arguments, then the predicates hold of one if and only if it holds of the other, and that would be all there is to say. There's like nothing really else interesting to say. Okay? But in the proof relevant setting, you have to remember that a predicate is a family of types. That's why I prefer to write it like that, which means these have not only just mere inhabitation as their relevant property, but they actually have structure. There's a bunch of proofs here, and those proofs have structure. And what we're going to say as I develop a little bit further, that the structure of the proofs of B of A is very closely related in really the closest, in the tightest sense that you could really ask, is very closely related to the proof structure over here. So we will end up saying something much stronger than that, okay, than mere logical equivalence. So that's why I am bringing it up this way, is because this is a sort of this will end up looking like although it's like sort of very standard practice in ordinary textbook, elementary math, in a proof relevant setting, these sorts of things start to look rather shabby because you think, well, you're clearly not saying enough here. I mean, you should be able to say more. And so we'll be talking about that. Okay, so that's the setup. Now I wanted to, okay, so that's where we were with the identity type. I'm going to pick up with this very shortly, and what I'm going to do in a few moments is to start developing a bit more of the structure of the identities proofs and say more about these maps. So that's where I'm going. But before I do that, I want to discharge another aspect, because I was trying to build up the structure of what is called ITT, the intentional type theory, you'll recall, as I outlined last time. So what I want to do is kind of finish up ITT by introducing a last notion for the time being. There are a few other things I could possibly say, but anyway, this will be the core of ITT, by introducing this idea of universes. And then I want to say a few things about what we've got to help motivate you for where we're going. Okay, so there's the idea of universes. So, and it's related to various things, including something that is sometimes called large limbs. And I'll talk about, that's what I want to talk about now. So you'll recall is that the following situation came up with us before. The example that we talked about before is we looked at, so the general principle for an if is we end up saying if m then n else p, if we look as in a limb out of Booleans, that this has some type in the general elimination form has some type b which involves m. Okay, that was something where I'm just reminding you, I'm not going to rewrite the whole thing. Okay, so the point is that b gets to involve m. So an example of this kind of thing has already been used here, because what's happening is you'll notice that, well, this is not to do with Booleans, but I just want to mention, right, we have a dependent family of types like the identity. So I could say something here that involves identity types, for example, and where the m could involve in the identity types. But the kind of thing that we're looking at is, the example that we're looking at is something like this. I said, well, one of the possibilities that this situation enables for us, which is a little odd from a conventional programming language point of view, is to be able to write something like if m, then 17, which is supposed to be a numeral of type nat, and otherwise true, maybe, as an example. And in conventional programming languages, this would be ill-typed. You wouldn't be able to write that, okay? And the reason is that there would be presumably no type that both contains the numeral 17 and the number true, the Boolean true, because we have a discipline of abstraction here. So these are not coded up as certain sets, and therefore you could find some union of those sets that contain both numerals and Booleans. That's not the game of type theory. In type theory, we respect type abstraction. So there's nothing sort of you could write here. But it sort of begs the question. I mean, the question comes up here. It suggests the question, well, if b can depend on m, I mean, why can't I write here, and I think I mentioned this to you before, something like this that says nat and bool. Maybe that's what I will do. Okay? And if this were a well-formed type, then everything would be fine, because the subsidiary requirements, if you look at the elimination rule, for this to be true requires two things. That for if true, 17 true, to be if true, you propagate it at bool. And so that isn't what I meant. Okay, what I meant was I need that to be in here. Okay, and this is definitionally equivalent to nat. And the other obligation, if you look at the elim rule, is that true should be in if false, nat, bool. And that's definitionally equal to bool. And we're good. All right, that's a well-typed term. If only we could form this. Okay? The question is that a type? And as of this moment in my development, it's not. Okay? Because the only types that we had that could depend on, the only non-trivial families that I've given you so far are the identity. So there would be like mn or something. That's a type that, or on some type A, whatever A might be. So on some type A, mn is the only way the m could involve in here, okay? And that, in the kind of scenario I'm looking at, the identity isn't involved. And then, as a matter of pure ad hocery, in order to illustrate a point, I gave you also the vectors of a certain length, okay, or sequences, I think I called them. Okay, the sequences of a certain length, and I did that as is purely an ad hoc exercise, okay, in order to like be able to write something useful at the board. Okay, so that's all we have so far, and there's no other way at this moment to introduce any dependency into the type theory. That is no other way to write down a family of types that involves a term, let's say, of type Boolean, for example. This one wouldn't. To involve Boolean, this would have to be bool if I wanted to do this, and to involve seek, well, that wouldn't happen because M is the wrong type in this scenario. So we're in a moment in an impoverished state. So on the other hand, it seems fairly clear that this is a reasonable thing to do, and in fact you might even say to properly exploit the possibility of the dependency of a family on a term, that I ought to be able to compute the type. See here, there's no computing involved, you just plug it in. Okay, it's a relation, it's a primitive relation that every logic has, equality, and you just plug it in. But you might reasonably say there should be a way to compute types, and that's what I'm trying to do here, is I'm trying to compute which type is it as a function of M, and since M is passed in, that seems perfectly fair game. So if you look at the rules of type theory, and remember, for those of you who know more than I've lectured on, where we are right now, there is no way to write down this type, okay? And what is the reason for that? Well, the reason is that recall that the rule for conditional says if, well, it's really implicit up here. The point is that there has to be a type, a motive, that we could write down. So we need the motive. So in order for this to work out, we have to have the following thing has to be a legitimate motive. And it isn't, okay, because this is an example of an A, so to speak. This is a type, okay, and this is a type, and it's not a term. So the thing that would go in the branch here of an if has to be a term, and yet this whole thing is supposed to be some kind of schema for a type. So we're in this weird situation. Okay, so if I really were to write it out and write the motive for the if here and be really careful, that's what I would write in those brackets. Okay, which I haven't done yet. Okay, so the question. So now there are two approaches to this, so you know. So the two approaches are a somewhat ad hoc approach, which are called large eliminations. Okay, and this is my personal opinion, is this is a somewhat ad hoc way of looking at things. Okay, and the idea is you just say, okay, I rule such things into the type theory, and I say, for example, let's just do it for Booleans because that's what I'm using as my example. So what I will say is, if I have this, okay, and then I have I'm thinking about what to write here. I have a function, let's write it like this, f(x) of a, f of x, let's just emphasize it is a type, okay, and then what do I want to know? Well, what I want to end up saying is, okay, if with a suitable sort of motive, M, what am I getting at here? Give me a moment. What I want to be able to say is that if A, B wants to be a type. Yeah, so that's what I'm going to do. So I don't need this. So what I need is if A is a type and B is a type, then if M, A, B, if whatever, you could write it down if you'd like here, but there doesn't even need to be it. In fact, the way to do it is like capital F. Let's write it like that. Okay, I'm going to get rid of all this in a minute. That's why I'm a little like not clear exactly what I'm doing. Okay, because this is this kind of ad hoc thing, and I'm going to get rid of it. Okay, so the ad hoc thing is you introduce a new form of type. Let's call it capital If for the sake of discussion. And the idea is that a capital If MAB chooses between two types based on a Boolean. That's it. You just do that ad hocly, and you have the obvious definitional equality rules. This is A. This is B, and that's pretty much all there is to say about it. So there are some versions of type theory where people do this, okay, because they don't want to do the next thing for other reasons, okay. So this is the typical thing. So one way to solve all this problem is introduce a special notion of capital If. We won't do that. Eventually, what I really wrote will be valid, but we'll write a special notion of capital If, and those are called large eliminations, because they eliminate into the universe. You have to use it. The universe of all types. Okay, that is you could almost say the type of this is type. Okay, and so these are types. So they're kind of eliminating into the universe of types. That's the way people think about it. Okay, so that's a method that people use in order to be able to type check programs like that. But there's another way which has a lot of benefits for other reasons besides just larger limbs, although it is one of the main benefits of doing it, is to introduce the notion of a universe of types. And that's what I want to introduce next. So it's difficult to give a definition of what is a universe. I can show you, here's a thing which is a universe, and here's this other thing which is a universe, but it's a little hard to say what qualifies as a universe. So I will just say, informally here, a universe is a type of types. That's what I will just say as my informal definition about what is a universe. A universe is a type whose elements are themselves types. Now, I'm not going to go into all the ins and the outs of this. There are actually variations about how you formulate what is a universe, but I'm going to do the one that is most technically convenient, and I'll leave. I don't think I'm going to devote a whole lecture to talking about all the different ways you could do universes, okay? But the idea is that it's a type of types. Now, no doubt, those of you with some experience are immediately thinking, this has to be suspicious, okay? Because we all know that there's like no set of all sets, okay? And so, like, what's going on here? There's something a little suspicious. Well, I don't say that it's the type of all types. I say it's a type of types, okay? So that's the idea. So what I will do, I'll start with one thing. I'm going to actually have to generalize this. We're going to introduce a base type, which is called U, and definitionally, of course, equal only to itself. So we're going to introduce a new base type, which will be called U. And this is going to be a particular sort of universe, because the notion of universe, as I'm suggesting it to you, is so loosely specified. I could basically stop here because I give no inhabitants to this thing, and it's, of course, therefore, it's a type of types. But so I want to be able to do. I want a particular sort of universe, which is in a certain way complete insofar as it possibly can be. And what do I mean by that? Well, what I'm going to do is I'm going to populate this universe with elements that correspond to almost all of the types that we've considered so far. Okay? So what I'm going to do is this. I'm going to have the introduction rules. So what happens is what I were previously calling the formation rules become introduction rules for the universe. Okay? So I'll write down a couple of examples just to be illustrative. So, for example, I could say that nat is an element of U. So this is now universe introduction, right? Because I'm saying the type nat is an element of the universe U. And I could say lots of other things, but I'll throw a few like illustrative examples down. And an important one is if A is in U and M and N are in A, then the identity Mn is in U. So this is another U introduction. So I could call that U introduction id if I wanted, and nat if I wanted to be like systematic about the naming. Okay, so I would do that. And then I would say the universe, well, this is the beginning of a closure property, that the universes are closed under the type formation operators in the following way. So the identity of a universe, an element of the universe, is itself an element of the universe. Okay? And then I could do something like this. I could say if A is in U, and given X in A, B is in U, then I can say that pi x in A, B is in U. Okay, so the universes are closed under the formation of pi, and while I'm at it, they're closed under the formation of sigma as well. Let's see, what else did we have? You would expect also, 1 would be in U, or unit, or whatever I called it, and 0 would be in U. And you would also have that if A is in U and B is in U, then A plus B is in U. Okay, written like that. And is that all the types I've done so far? Anyway, if it isn't, well, there's the ones that are special cases, arrow and cross, so we've covered those. Identity type, let's forget about the seek, that was just thrown in there for illustrative purposes. So we do all of that, and we put all that. However, you can smell this one coming, okay? I do not postulate U is in U. Okay, that's no good. Okay, can't have that. Okay, so it's almost as if I just said take all the formation rules and turn them into (U), and then that's going to be the definition of U, except for the fact that here's a formation rule. This is a universe formation, and that one doesn't at this stage get to be turned into an introduction rule. Now, I'll give you this to play with for homework because it's a fun little exercise to work out. You certainly smell that this is not going to work from your private experience, but I thought I would have you figure out in type theory why it doesn't work. And the idea is that you can reproduce the Burali-Forti paradox, if you know what that is. Can be reproduced inside of type theory. The Burali-Forti paradox amounts to the following observation in set theory. If you take the class of all ordinals, it behaves exactly like an ordinal, except for the fact that it's not a set. Okay? And it better not be a set, because if it were, you'd get the paradox. And so what you do is, by a similar reasoning, so to speak, the class of all types cannot itself be a type. That's what's happening here. If you were the class of all types, and it cannot itself be a type. If it were, it would have to have itself as a member. And so the way you do this with the Burali-Forti paradox is you introduce the notion of a well-ordering, and you end up constructing the well-ordering of all well-orderings, and then derive from that a contradiction. So I'll have you look at, we don't use ordinals. In constructive theories, the ordinals do not form a linear ordering. That's a classical kind of principle. So you have to deal with well-founded things that are like more tree-like, but well-founded, but not necessarily linear. That's a difference. But otherwise, if you do it constructively, you can reproduce the Burali-Forti paradox. So this is not the case. Okay? So that's the sort of introduction rules for the universe. So if I had those introduction rules for the universe, then this guy is okay again, because I can sort of reproduce this thing, because I will be able to show that if nat, if m, then nat, else bool, will be in U. Okay, and given something else I have to do, but the idea is that, first of all, I can now form this thing without you. Now let's forget the larger limbs now. I can now form this thing, whereas at the moment I introduced it for the purpose of the lecture, I was not able to form it. I can now form it because the type of the two branches, there is a common type, and it's U, okay, which doesn't depend on M. Okay, it's just a constant, okay? So this is like this. Why? Because nat is in U and bool is in U. Well, bool is in U because 1 is in U and 1 plus 1 is in U, and bool was defined to be 1 plus 1. So we get nat and bool are both in U. Okay, so then we appear to be off to the races. Except we have to have also some elimination rules, because it's well and good to form that thing, but what allows us to classify things, other things, using the universe. So this is a technical device now that people use. So the thing is, is that, actually, no, we're fine with this. Everything is fine. These are types, and the elements of the universe are types, and that's basically all you need to know. So, in other words, yeah, I'm anticipating a slight technical issue that I'm going to dodge, but let me try to do it here. So the way I formulated the universe is the type nat literally is an element of U. So in some sense, the type nat has a dual role. It's a type, but moreover, it's an element of U. Okay? So let me just mention briefly, without going into details. Sometimes, for various technical reasons, people prefer to say, no, it's not really nat that's in U. What happens is there's a code for nat. We'll write it, sometimes people write a dot above it. Nat dot is in U. And then you define a decoder that says, oh yes, nat dot is in U. And by the way, if you look at what nat dot stands for, it's written T of nat dot, that's nat, etc. So this is the name for the type, and the elements of the universe are the names for the type. And then this is a denotation thing that says that this code names the type nat. And you do that in a systematic way. And it's a bit persnickety. And one of the things about it is, you'll notice, is that this is a kind of a large lim. Because what I'm doing is I'm saying there's a map from U into the space of all types, and it's defined by some equations. So that's what sometimes people do when they formulate universes. I'm not going to do that here. I'm going to be, like you could say, I'm going to be loose or cheating, okay, so I don't have to worry about it. So the idea is then this is a well-formed thing, and it has these definitional equivalence rules. Mentally just turn that back to lowercase f. These things will have the same definitional equivalence rules that they always do, and since the elements of the universe are types, then I can use them in this position, and they classify things, and everything works like very nicely. Okay, so that's the first thing. So I gave you some exercises. So now I gave you some exercises last time. Rely on the role of universes, and there were two of them that I swapped. I remembered correctly the issue, but I forgot which one provoked which. Okay, so I gave you as exercises, and I'll remind you. So the injectivity of successor. Okay, and this you can do fine. And the idea is that the successor is not zero. This you need a universe. So I said to you at the time when I wrote it down, you won't be able to do this now. Okay? And when I said it, what I said is I said it about this one and said you could do this one, and it was exactly backward. Okay, this is the one that you're going to need a universe for. And there's a theorem by Jan Smith from 25 years ago that says you really do need U. If you take the type theory without universes that I have so far, you can't prove that the successor is non-zero. I mean, it's independent. So that tells us that adding the universes is adding expressive power to the language. And there's a similar thing that I gave you, which was to define first and second from, I think I called it split, the sort of positive elim form for pairs. And again, here you'll need a universe. Okay, which is the thing that I was foreshadowing. Okay, you'll need a universe for this. Okay, you'll see why. It's very easy. As soon as you write it down, you'll realize what's going on. Okay, so you'll need a universe for that. So that's just a mention. So that like discharges. I made some dark comments when I introduced that, so I wanted to make sure I made clear what I was saying. Okay, so now there's something about the type theory. Now, if we work the type theory this way, this lets us do a lot of things. However, yeah, go ahead.
I'm wondering if you forget about the refraction rule.
Speak up.
That if there's an element in U, then that element is a type.
M, N, and U. This should be an A. Is that what you said? Yeah.
No.
So what was your question?
The general refraction rule, saying that if something is an element of
U. Well, that's what I was alluding to. So this is a similar thing. I could write a rule. Yes. You're saying, do I need the rule? I need to write it somewhere. if M is in U, then M is a type. M is a type. And what I'm saying is that you could consider taking that as a rule, and the same thing for definitional equivalence. You could consider taking that as a rule, okay, but it's admissible. In other words, if I said a universe is anything that contains types without being very let's see, how do I want to say this? The rule will be admissible because if you look at the way in which you could possibly derive M is in U according to the rules I've given you so far, by an inductive argument you could say here A is a type, M and N is an A, therefore that's a type. And by an inductive argument, A is a type, therefore this is a family of types, and therefore that's a type. And the rule would be, this principle would be admissible. Oh, yeah, that's what I would say, yeah.
Well, if you're trying to subsume the large limb rule,
yeah,
then you can also produce other elements from like the elimination rule or for example, if there's no such rule for if, but now I can form an element in U by using if.
I think you're going to say what I was just about to transition to, but...
Oh, I see. So that's the one I'm not sure.
Okay. So this does not replace that. Is that what you're asking? That's what that's what I'm about to explain. Okay. All right. So the thing I just erased the board for is this. Okay. By introducing one universe, I've really only solved the problem at hand without really solving the problem. Okay. And the reason is, because I cannot take U as in U, I can now just reproduce this problem at another level, right? Because I can now talk about, well, what I want to talk about is something like this. I'm going to have situations like this where I can have, I'm interested in U and U arrow U, which maybe if I use that convention of a capital letter, if I had large limbs, that would be a perfectly valid type. Because U is a type and U arrow U is a type. And so by the principles of, and this being a bool, again, for the sake of discussion, then the large limb would say this is a type. Okay, so that's what the large limb would do for us. But these things are not themselves inhabitants of U, so I can't use the same ruse. Right? I'm back in the same boat all over again. Okay? All right? So you might want to say, well, so now what do I do? So one approach is you just say, well, you just live with the idea of larger limbs. That's it. And you do that. So some people do that. You can do that. But if you look in the hot book, we did a different thing, which is also the thing we did in New Pearl a long time ago, which is what we said is this, which we say, okay, yes, it's true. Out of the frying pan and into the fire, okay, I tried to figure out, a way around this problem, and then I just introduced another version of it at a higher level. But now there's a little game you can play. And you say, okay, here's the idea. I don't have one universe, I have a cumulative hierarchy of universes. And now I will win. Okay? At the expense of doing this. So a cumulative hierarchy of universes. And in fact, whenever you look at presentations of type theory, at least basic ideas of type theory, they always have a cumulative hierarchy of universes. And the idea is this. You say, okay, what I want to do is I want to get rid of this business about A being a type altogether. Okay? And I want to say there doesn't exist the notion of A as a type. The only notion there exists is being an element of a type. And you say, well, wait a minute. But then to be an element of a type, then you must have a type, right? So what does it mean for it to be a type? Oh, it means to be an element of a type. Okay? And I do that to infinity. So the way you do this is, what you say is you have a bunch of universes, UI, which are in UI plus 1. So this could be thought of as UI plus 1 introduction. Something like that. So that the U over here is U1. Okay? That's the one way to think about it. So you just write this down. So you have a cumulative hierarchy of universes, U0, U1, U2, like that. And you say each inhabits the other. And that's the first critical notion. And it's an atom. It just doesn't have any trivial, it has only trivial definitional equality. So you do that. And then you introduce closure principles for each universe. Okay? So we end up saying, for example, we say NAT is in, let's say we start at 1, NAT is in U1, okay? And then et cetera. Let me just write one other example just to be specific. So we can say, oh, in fact, you can do it like that. No, what you do is you say NAT is in every universe. NAT is in UI. And you say if A is in UI, and and given X in A, B is in UI, then you say that universe is closed under the general product. So that's UI as well. And so is sigma, etc. Except we now have this principle. Instead of U colon U, we have UI colon UI plus 1. And then we have one more, which is the principle of cumulativity, which says that if A is in UI, then A is also in UI plus 1. And that's called cumulativity. And in fact, you then also say if they're equal as elements of U, definitionally equal as elements of UI, then they're definitionally equal as elements of UI plus 1. You have both, and that's called cumulativity. You have a cumulative hierarchy of universes. So this is forced on us because of the Burali-Forti paradox. This architecture is forced on us by reasons of what is called, so this introduces what we call the size hierarchy. And those of you who know about such things, these basically correspond to the idea of inaccessible cardinals. Okay? Because what we're doing is, with the idea of an inaccessible cardinal in set theory is you have a cardinal in such a way that V sub that kappa is completely closed under all the things that you postulate for set forming, in particular power set, what's really important, power set and replacement and the natural numbers and all the axioms of set theory sort of hold in that approximation to the universe of sets up to that cardinal, and an inaccessible cardinal is one for which that holds. And then you just, to increase your expressive power of your set theory, you just start throwing in axioms of more and more outlandishly inaccessible cardinals. Okay, the first one being omega, the natural numbers itself. If you take set theory without the natural numbers, then omega is an inaccessible cardinal. You can't get to it without by iterating all the things you've had already, and so you throw that in, and then later you throw in others. So these universes things they're analogous to, let's say, I would say they're analogous to large cardinal axioms in set theory. Okay, so this is what is called the size hierarchy. Okay, so it's unavoidable, and I'm going to write it. I'm going to draw a picture later, or I'll start drawing it now, which is the hierarchy of things if we have U1, U2, U3 up here, going like that, which is a collection of universes. So you can say that the universe of types is being stratified, okay, by considerations of size. In the same way that the large cardinal axioms can be thought of as indexing, notions of size of sets, okay? Then you can get bigger and bigger sets. So that's what is going on here. And then what we're going to do now is we're also going to introduce a horizontal axis, which is a new thing, which is going to be called the idea of level, H level it's called, or dimension. And I will start talking about dimension now, but I haven't gotten to this yet, so I'm foreshadowing. But there's going to be another stratification, which I like to think of as being on another axis, which is of dimension. So the dimension and the size hierarchy are going to be kind of different. Two different notions, although they are related. So things of large size tend to have large dimension. But there are things of small size that have large dimension, and or you could say it the other way: large dimensional things have small sizes. That is definitely true. So it's not like they're related but not totally coupled. Okay, so what we'll do is we will distinguish these two. So in type theory, traditionally in type theory, we've always had this hierarchy of sizes, and it's only recently that we've developed the idea of dimension. So that's the new factor. So this is the new thing in what we're calling HoTT type theory. Okay, is the idea of it is introduced this idea of level or H level or dimension. So that's why it is sometimes called higher dimensional type theory. Okay, so that's the notion of universe. Okay, so what happens is, and I'm not going to write it all on the board, but what happens is if you look in the HoTT book, for example, okay, yeah, I should mention one other thing, which is the notion of typical ambiguity. Okay, which is, in the HoTT book, we often write, let's look at this rule. The formation rule for pi's now looks like this. It says if A is in U, and X is in A, then B is in U, then pi X in A, B is in U. I want to explain to you what this rule means. Okay, so previously we said if A is a type and this is a type, then that's a type. Okay, that's all good. But now, in order to take advantage of this, there's this technical device of using a cumulative hierarchy of universes that lets me get rid of the judgment of something being a type and replace it by being in U. So that means that throughout the book, or whatever, you'll see that the formation rules, so pi formation is just the same thing as universe introduction for pi. Okay, so that's a short form for that. So that's the way it works. But now there's one thing you have to understand. And the thing you have to understand goes back to Russell and Whitehead, which is called typical ambiguity. And the idea is, what this really means is, pick any I you want, the same in each of these places, and then this will be a valid rule. And the implementations of type theory use an algorithm, type inference algorithm, for resolving these levels, okay, and doing it for you automatically. Now, I'm not sure. It's either in a fork release of Coq or it's in the general main release of Coq. I'm not positive, but it just got introduced this past year. And the idea is it lets you do this kind of thing ambiguously. So you write them down ambiguously. It's simultaneous. So it's a kind of universe polymorphism. When I introduced this thing, it was called universe polymorphism. Okay, and in Russell and Whitehead, it was called typical ambiguity. So this is also called universe polymorphism. And what's really fun about universe polymorphism is it lets you pretend that you have U colon U, and it will automatically figure out that this has to be I and I plus 1 for you without worrying about it. Okay? And in fact, it's kind of an amusing exercise. It's very difficult to write down a piece of code that gets you a proper violation of that really forces you to be in U, and therefore gives you a violation of the universe. So what happens is it ends up being constraints. So the way you do this is I, this is J, this will be K, and it puts the constraint that K has to be at least I, the max of I and J. Because by cumulativity, I can push either one of these up to the max, and then use the closure and get that to be the max, and I can't do it for anything less. So that's what it actually does. Okay, it works like that. So what happens is when you're type checking is you have to solve these systems of constraints. And it's damn difficult to write down a piece of code for which this has no solution. Okay, so in practice you can pretend U is U and you'll never notice the difference. However, there is one example you can do where you will get a universe violation, which is if you formulate the Biroli-Forti paradox, it will indeed tell you that the constraints are unsatisfiable. And in fact, when we first did this, we spent quite a while trying to find simple examples that would violate it, and we never could. So we finally just said, okay, we'll just do the Bialy-Forti paradox, and then it damn well better say no. And it did say no, so we were happy. So we thought it actually works, so it was good. But you have to go through some effort, okay, to make it work. So there's this game here, which is actually, in a certain degree that I'm going to explain, reproduced on the H level, if you're always putting everything off to some higher level. So being a type just means to be a type of a higher level, which of course is a type of a yet higher level. And since I have an infinite hierarchy, then somehow that makes sense. Sometimes I wonder. But yes, I think that basically makes sense. Okay, so now at this point we have introduced ITT. Okay, so, or at least a substantial fragment of it, which is we have the sigma pi identity plus n universe. So let's just write it like that. Okay, so that's what I care about. Sometimes people do another thing called W, which I will get to a little bit later. I'm just deferring that. So the core of O and NAT, we'll have NAT in here. NAT ends up being an instance of W later. Okay, so that's the type. That's called intentional type theory. So Martin Liff introduced essentially this in like '73. Okay, and everyone ignored him for a long time. So that's like the kind of the history of it. So Martin Liff introduced it in '73. And so what I want to do now is, in order to make a transition, is I want to make a few remarks about ITT that I might have like slipped by you, that you might not have noticed on the fly, because it's easy to assume or think, it's easy to jump to conclusions that aren't quite true. So let me mention one, which is just a very simple thing, which we'll come back to later. So I'm going to do some little elementary properties of ITT in order to motivate a few things that come later. So the first thing, inevitably this is always the first thing, so we'll do this, which is the axiom of choice in ITT. Well, actually it's a theorem. The theorem of choice. Okay, so we'll write it like that. And what does the theorem of choice say in ITT? It says every total binary function relation contains a function. Okay, that's all. So what I say is, if for every x in A there exists a y in B, okay, such that C, some relation, holds of x and y, then there exists a function from A to B such that for every x in A, C holds of x and f of x. And f is called the choice function. What is called the choice function? Because the idea is that if C is a total relation, meaning anything in the domain is related to something in the codomain, so the picture you have is you have x here, and, well, there could be a bunch of y's, but anyway, there's always one. Okay? There's always one in here, and you do this for each x. There are a bunch of y's they're related to, but anyway, there's one. Okay? Then you can pick out a canonical one, that's the way to think about it, which is a representative of the things that it's related to, and f does that job. F says, pick out one from here, one from here, one from here. So these are x and x prime, etc. So pick out from one from here, da 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 da. That's what this is saying. Okay? If there's always one, then there's a canonical one. F is the canonical choice function. So when read in ordinary classical logic, where this would be that, and this would be that, and this would be that, okay, it's independent of the axioms of set theory. That's very famous. Okay, that it's not something you can prove. But in type theory, in what I have so far, it's simply a theorem. Okay, and I'll tell you why it's a theorem. Okay, the reason it's a theorem. Okay, why is it a theorem? All right, why? Why is it a theorem? And the answer is because of proof relevance. Because it's a constructive theory. And amongst other properties of constructive theories, proofs are relevant. So the idea is, let me just do it informally rather than write down a full derivation. Give me one of these, let's call it capital F, okay? Because that's my hypothesis. I need to say, the proof I want is going to say, give me one of those, capital F, I won't write down the type, and I'll give you one of these, okay? And so let me make some room for myself. So to give me one of these, I want to write down an ordered pair, right? Which is the F from A to B here. So this is going to be lambda x, that's in A, and I'm going to write something here, and then I'm going to write something here. Okay? So the proof of this, of the theorem of choice, is going to be this lambda term that I'm going to write down. And the question is, what is the choice function f that I'm going to write here? Well, what do we know about f? Well, what I know about f is if I apply it to x, right, then I get an element of this type. Exists a y and b such as c of x and y for that particular x. Okay? So if I write it down here, it will, right? That's the spec for f. It's a function that gives me back one of these. So what I do is, if I want to know what is the b in question to which x is related, well, that's none other than first of f of x. So I've written this down before. And now I need to prove that for every x in A, it's related. So I have, give me lambda x for every x in A. Now I want something of type c of x and f of x. Where am I going to get that? Well, if I look at capital F of x again, it's a pair. The second component of f of x. What is the type of the second component of f of x? It's going to be c of x and the first component of f of x, because that's the typing rule for second, okay, which I gave you before. And first of f of x is indeed that first element of that pair, so it will indeed be an element of that sigma type, and it works. Okay, do you see it? So I approached it as a functional programming exercise. So if you go, woo-woo, axiom of choice, uh-oh, I know to be afraid of that. But if you just like step away from that and just say, I'm just writing a functional program, is there a functional program of this type? Well, I basically don't even have to think. I just write down the only thing I pretty much can do. That's typical of functional programming. As soon as you write down the type, the code writes itself. Okay, I don't have to worry. I don't have to worry about it, what to do. And that's the beauty of functional programming and why it will win in the end, always and forever. Okay, so this is the example. But what is odd about this? You can say, well, how come more or less modulo notation that proof doesn't work in set theory? Okay, that's a good question. Because in set theory, okay, I would have used for all, I would have used exists, okay, that's notation. And this is notation. I would have written implies. I know a lot of people write arrow, but never mind. So I would write implies, okay? The difference is, in set theory, you don't get to treat the proof of the antecedent as a piece of data that you then manipulate in the code and the result. So what I did here is I have a hypothesis f. So f should properly be thought of as an assumption that this is true. In other words, it's a generic proof of this fact, which I'm assuming exists. And then I go right ahead and muck about with it as if it were data. Okay? That you can't do in set theory in conventional first-order logic. It doesn't exist because proofs are not objects. Okay? They aren't, in other words, they're not mathematical objects. Okay? So because they're not mathematical objects, I don't have this f around to write a function which mucks about with the proof and extracts it and reorganizes it to put it in here. So that's like one way to think about what is going on here. So proof relevance is key. Okay? Without proof relevance, then the whole thing is a not starter. A little bit later, what I'm going to do is I'm going to reconsider the example of the axiom of choice. But what I'm going to do is I'm going to introduce some suppression brackets. What I'm going to do is I'm going to put, like, we usually write them like a double vertical bar here on the outside. And as we will eventually see, the meaning of the suppression brackets is to stipulate that this be true without revealing the proof to you. Then we're in a whole nother ball game. And you can no longer, in that scenario, you can no longer extract the F from the capital F, and then the thing will in fact be independent. So the thing I'm heading toward is, one of the things that's very beautiful about type theory is when you introduce distinctions, you can selectively, eliminate them and recover the traditional way of doing things. So in other words, when I introduce proof relevance, a special case of proof relevance is proof irrelevance. Okay? Whereas if I start out the entire enterprise with proof irrelevance, that's like not even an axiom, it's the whole framework of set theory. The first thing you do without ever considering it is you write down first order logic. You've already said proofs are irrelevant. Well, now it's hopeless. You can never get back. You're screwed. Once proofs are irrelevant, then that's it. You can't get back to relevance. But if you say that proofs are relevant at the outset, then you can selectively suppress the relevance of proofs and get back proof irrelevance. So the constructive framework is strictly superior. Okay? That is the idea, because I can reproduce all of the reasoning that you're familiar with and point it out as a particular kind of degenerate form of what you might have done in the fuller type theory. That's where the power of type theory comes in, okay? Is that it gives you that. And this idea comes up a lot. The same thing comes up in programming languages. There are loads of people who wish to deny you the ability to make type distinctions by calling their language dynamically typed. And then they somehow, and then you're screwed, you see? Because if you have a static type system, a dynamic type system is just a mode of use of static typing. If you insist on dynamic typing at the outset, then what you're doing is you're denying me at the outset the ability to express type information. And now you're screwed. You can never get back. But if you start here, then I can selectively suppress that information and get down to a dynamic type system as a special case. It's strictly superior. Now, I know that there's, if you say that on Reddit, you'll get flamed to death. Okay, but nevertheless, it's true. So, as an example, there's a funny thing that happens that somehow people specify the weaker thing as being stronger. I'll never understand that. Okay, but it's a well-observed technical fact. Okay. So that's like first thing. So that's just for fun, and we'll come back to that a little bit later. This next thing you're not going to like at all, I don't think. Okay. And it pertains to what I'm going to do. Okay, let me just check. Yes. So it's a theorem of Martin-Löf's that I'm not going to prove here. That if you have a proof of an identity for closed M, N, and A, in other words, you have an absolute, you have an absolute proof of an equation. In other words, there's no hypotheses around. That's all I'm saying. If I have a proof that's not under hypotheses, okay, so I have no hypotheses. So I just have, in the ordinary parlance, a theorem. If I have a theorem, then M is equal to N in A, whatever A is, okay, and P is the proof of that theorem. Then here's what you're not going to like. M is definitionally equal to N in A. So this is a theorem of Martin-Löf's. In fact, I believe it's even in his original 73 paper, if I'm not mistaken. Okay, which tells you this. Now, unless you've thought carefully about things, you might be uneasy about whether you should like this or dislike it. So let me explain an example of this. And then you will, I think you will then agree that you will dislike it. Okay, so for example, suppose A is nat arrow nat. Well, no, I'll do it nat arrow nat arrow nat, like that. And M is lambda x, lambda y, x plus y, our favorite example. Lambda x, lambda y, y plus x. Okay? Where plus is defined by recursion on the second argument. We'll pick one, whichever one it is. Okay? For some reason, I always do it on the right. But okay. So that's what I mean by plus. Okay. If you take this, so what does this tell you? Okay? What this tells you is that you have to run it backward. These are not definitionally equal. Okay? And therefore, there's no proof that they are, yes, therefore, there is no proof that as elements of nat arrow nat arrow nat, there's no proof that they're equal. And now I know what you're thinking. You're thinking, wait a minute, you just told me last lecture that these two things are equal. I know. Hold on a second. Okay? There's no proof term. There's no P of that type.
Oh, well, sorry to interrupt you, but the truncation of...
Oh, did I make a mistake over here? We're backtracking. Okay, what did I do?
It should be pi x a, like the assumption of the class will the non if you try to mimic the classical version, then that will be pi a and then truncated.
Oh, okay. It doesn't matter. All I was trying to do is say, later I will do some additional things in which I can make this more subtle. Okay? That's it. I made my main point and I stick with it. Okay, let's not get derailed on that. Okay, so there's no proof that these two things are equal. Yet, I showed you and gave you for homework, given x, y, and z in that, there exists a proof P, which I gave you for homework, that id nat x plus y and y plus x. I gave you that to look at. There exists such a proof term. And so now you definitely think I'm nuts. Okay? Because I'm telling you, for every x, y, z in nat, x plus y is equal to y plus x. There's a proof for that. You can write that down. We discussed that. Yet, you cannot conclude that the corresponding functions are equal. I cannot discharge those hypotheses. Okay? So what does that mean? What is called the axiom of extensionality fails. Okay? It is not the case that if uniformly in X, I have a proof, let's see, B, f of X, f of Y, f of X, g of X, what I want. F of X, g of X, right, yeah. Then, so this is not true, okay? Then something is a proof that id A arrow B, f and g. This is not the case. In particular, I cannot even get lambda x f of x is equal to lambda x g of x, which is an eta step away from f and g. I can't even do that either. Okay, in fact, you could argue that that's exactly the thing you can't do. Okay? So that's not very nice. Okay? This is not very nice because it means that your ordinary notion of function which you may well have taken for granted, like somehow without thinking about it as I went along, that surely this is true. Unfortunately, it's not. Okay? And this is one of the many weaknesses of HoTT, okay, is that axiom of extensionality fails. Now, in order to, so you might say to yourself, oh, fine, take it as an axiom. So one thing I could do is, there are different versions of this, of way to do it, but one version of this is you say, essentially, lambda x dot p with an abusive notation should be a proof of id a f g of, well, id a arrow b, lambda x f of x, lambda x. In other words, lambda x preserved, p is preserved by lambda abstraction, so that if I have a family of proofs like this, I should lambda abstract it and get a proof of these two things. And then by eta, those are definitionally equivalent, so I would get extensionality. So you might think what you should do is add in a new axiom like this. Just throw it in. The problem to worry about is, what is poor J supposed to do when it sees lambda x dot p and is trying to do an x dot q? What is it supposed to do? See, because remember, J depends on the idea that its beta axiom only applies to reflexivity. So if you now start chucking in new proofs, I put it in quotes because I'm trying to, emphasize the somewhat dubious nature of throwing in axioms in type theory. If I just throw in an axiom like that, okay, then I've screwed the computational interpretation, because the beta rule, there was a beta rule for REFL, we were good with that. So we had REFL of m, and we said that was equal to m for xq. So that's good. But now we have this instance of axiom of extensionality. That's another sort of proof. And what in the hell am I supposed to do with that? This is the number, in my mind, the number one problem with homotopy type theory. Because in homotopy type theory, this term will be definable in terms of other things. So for the temporary purposes, I might as well say, we throw this in as an axiom. And when you throw it in as an axiom, you've completely screwed the computational behavior, okay, of what's going on with J. And the big open problem is to understand the computational meaning of homotopy type theory. And this is the beginning of why it's an issue. Okay? So that's the first thing I want to mention to you about that. Okay, so we'll come back to this very shortly. We'll start talking about the structure of identity proofs, but that's the issue. But right now in ITT, the axiom of extensionality fails. Okay, and so that has created a lot of problems. Okay. So there's one thing that I want to say about this. Do I want to say it about this? Yes. No, I won't say it right now. Let's leave it. I'll leave it alone for the time being. Okay, I'm going to come back to the meaning of the axiom of extensionality in a minute. Okay, so third point I would like to make is to define for you what is ETT, which is the extensional theory of types. Okay, ETT. So the word extensional is overused in type theory, so it has many different meanings. The meaning in this case that I'm going to explain pertains to that, but it's not wholly about that issue. It's about other things. Okay? And here is the idea. So the idea is that, the way I like to think about it is this. Let's hold in abeyance this principle about function extensionality. That's what it's called. So to be precise, people will often call this function extensionality to avoid confusion with other uses of the word extensionality. So that's called function extensionality. So the idea is, let's hold that in abeyance. Let's pretend I didn't say that. So the idea is that the only paths, the only identifications are reflexivities. if you look at the whole type theory I've written down, the only way you can get an element of the identity type, the only introduction rule, is reflexivity. So this whole thing is like some big charade where I'm going through all this stuff about showing symmetry and transitivity and transport properties and everything. And if you look at it, the whole damn thing always comes down to the fact that the only path there could possibly be is reflexivity. So of course you can transport between the thing and itself. So of course functions respect f of x is equal to f of x. Okay? And the whole thing seems like a big kabuki dance. And for a good 20 years, there was this kind of theological dispute about the nature of type theory, where we had, on the one hand, the advocates of ITT, and the other hand, the advocates of ETT, which I'll describe what it is. So what is the idea of ETT? ETT says, oh, please spare me, okay? If you have a proof, P, of identity of M and N, okay, then it can only be that it's reflexivity. So we can just conclude that M is judgmentally equal to N. And this is called equality reflection. And moreover, if you have a proof of the identity of M and N, then that proof can only be reflexivity. And this is called the uniqueness of identity proofs. And you can say ETT is defined by this principle. So this one only makes sense in the presence of that one, because once you have this one, then you know M and N are definitionally equal. And then it makes sense to talk about a path between M and N being the same as a path from M to itself, because we know that M and N are definitionally equal. So somehow the meat of it is right here.
The type on the second one.
Did I screw it up?
The type is like ID A and right on the bottom, where you have A on the bottom of that line. It's like ID.
No, this should be ID. Sorry, yeah, thank you. Yeah, this should be IDA MM. Let's say. Yeah, yeah, you're right. Yep, sorry. Yep. So this is where the meat is. This is where the thing is. Now, if you have this as your principle, then function extensionality is no problem. Why? Because by identity reflection, this is a definitional equivalence. And then, by the principle of congruence for definitional equivalence, we can put lambda x fx is definitionally equal to lambda x gx. And then with eta, that's f and that's g. So function extensionality falls out. So it implies function extensionality, amongst other things. This guy implies function extensionality. So it certainly gets you out of that bind. And not only that, it obviates the need for transport. Why? Because if you think of the rule for transport, the rule for transport says you have a family of types. Well, whether it's in U or not is not relevant here. And you have you have a proof that A is equal to A prime in A. Well, that means that A and A prime are judgmentally equal. And therefore, by the equality identity reflection, and therefore the types B of A and B of A prime are definitionally equal in U. So they're replaceable one for the other without any need for transport. Okay? And life is really good. Okay? If you want to formalize any kind of conventional mathematics, like very ordinary things that you run into every single day, okay, this is the way to go. And so basically, New Pearl was always based on ETT. And Coq has always been based on ITT. It has some doodads and extra things, but I'm trying to get the core issues here. The same is true. Same is true here. I'm just trying to strip down to one basic principle. Okay, and so the motivation is, as I say, that all there are reflexivities anyway, so it's just like absurd to be pushing around reflexivities and doing transports. And the experience until like a couple of years ago, the experience with doing things this way was every single person ends up complaining bitterly about the obnoxious need to pass around all these proofs of identities that are only reflexivities, and it gets really, really, really tedious. So, and whereas New Perl, we never had that problem. So let me mention the disadvantage. The only disadvantage is that the type checking relation, so here M:(A) is decidable, but not even remotely feasible. Okay. You can forget that. There are good lower bounds, okay. It's not even anywhere near feasible, but it is decidable, okay. Whereas here, and you can do this as an exercise, it's undecidable. So let me give you an intuition as to why it's undecidable. And then I'm going to argue it doesn't matter. Okay, it's undecidable. Why? Because in order to decide type checking as a subroutine, you need to decide definitional equivalence. And in HoTT, if you want to know whether M or N are definitionally equal, well, you can calculate, like beta reduce both sides and try to see if you can get them to be the same. But in the presence of identity reflection, there's another option, which is search for a proof. I want to know M is equal to N. I have to run this rule backward. And now I have to search for a proof. I say, oh, is there a proof of this? Oh, now I'm in arbitrary theorem proving. I have to prove, is this equation true? That equation, you can code up with higher types equations that represent open problems. I mean, you're not going to be able to decide, okay, whether these things are equal. So you can't find that P. So this relation is undecidable. However, what is perfectly decidable is that D is a derivation of this fact. That's decidable. If I show you a proof ending with M:(A), you can check that that proof is correct. And indeed, when you work with Calc, you don't actually write down M:(A). What you do is you run tactics and decision procedures to compute such Ds anyway. And those are the things you really work with. These are not the things you really work with. So at the level of opinion, in my opinion, this is like an irrelevant distinction. Okay? There is a relevant reason to distinguish these, but this isn't it, okay? My opinion. Okay? I've given you my reasons. The mode of use of Calc and the mode of use of New Perl are identical. And that's not a coincidence. Chet Murthy took the New Perl architecture and built Calc. The Calc you know today is New Perl, okay, rewritten, okay, and uses the exact same architecture. Okay, so that's where, so there's a direct causality here. There's a reason it looks like that, okay, because it works like that. So that's why they're both working in this. Now I see Kayvon's outside the door, so I'm way over time. Okay, so I will pick up next time and talk about, I had a few other points I wanted to make. Sorry about that. I'm running long, that's kind of rude.